we were discussing about electromagnetic induction, and we know that when we have a varying magnetic field we can produce EMF. That's electromagnetic induction principle. Like for example, if you have a coil, connected to a galvanometer and a magnet is moved away or towards the coil, you can see a deflection in this galvanometer. That is due to electromagnetic induction. Now here the magnet is moving. The varying magnetic field is produced by the motion of the magnet. Now in case if we have a stationary magnetic field or a constant uniform magnetic field, can we induce EMF? So that can be done by moving a conductor. The EMF can also be induced by moving a conductor in a uniform and time independent magnetic field. In a uniform and time independent, that is, the magnetic field is not varying with respect to time. Time independent, moving a conductor in a uniform and time independent magnetic field. And if the EMF is induced in this way, then it is called as motional EMF. The EMF induced by moving a conductor instead of varying a magnetic field is known as motional EMF. Now we will derive an equation depending upon the velocity of the conductor and also the magnetic field and the length of the conductor, and we will see how we can measure the induced EMF using these quantities. Now first we will write a question, and based on that we will derive the equation. A conducting rod PQ of length L connected to a resistor R is moved at a uniform speed V. Normal to a uniform magnetic field B. As shown in the figure. We will write down the figure later. Question number A. Deduce the expression for the EMF induced in the conductor. Deduce the expression for the EMF induced in the conductor. Question number B. Find the force required to move the rod in the magnetic field. Find the force required to move the rod in the magnetic field. And question number C. Mark the direction of induced current in the conductor. Mark the direction of induced current in the conductor. Take down the figure. cross represents the magnetic field which is going into the plane of the paper, or which is going away from you. This is a uniform magnetic field B, and in this field we are placing a conductor PQ. And it is connected to a resistor R. And moved in this direction with velocity v or speed v. Now deduce the expression for induced EMF. Let me read out. A conducting rod PQ of length L. The length of the conductor is L given. Is connected to a resistor R, is moved at a uniform speed v, normal to a uniform magnetic field B as shown in the figure. It's moved towards the right. Now deduce the expression for the EMF induced in the conductor. Find the force required to move the rod in the magnetic field. Mark the direction of induced current in the conductor. First we will take down question number A to find out induced EMF. Induced EMF. Now according to Faraday's law of electromagnetic induction, the induced EMF is proportional to the rate of change of flux linking the coil or the conductor. So to calculate the induced EMF, we should know d phi by dt, that is rate of change of flux. Because we know E is d phi by dt, that is by Faraday's law. So first we have to calculate what is rate of change of flux. As the conductor is moved, the flux linking the coil changes. Now in this case B is uniform, the magnetic field is uniform. Now how does the change in flux takes place? The change in flux is taking place due to change in the area swept by the loop. So given B is uniform or B is constant, given B is uniform, therefore d phi by dt or rate of change of flux is taking place due to change in area swept by loop. Change in flux is taking place due to change in area swept by loop. To calculate d phi by dt, first we will calculate what is the change in area. Now because we know phi is BA cos theta, and theta here, the magnetic field and the area vector are parallel to each other and the angle between them is 0. So cos 0 will become 1, therefore phi is BA. Now we will calculate what is the change in area. So for that we will take, let the lengths of horizontal arms of the circuit are lengths of horizontal arms of circuit are x1 and x2 at instants t1 and t2. respectively. So what do you mean by this? So let me show you the figure. Now we have the uniform magnetic field B, this is the uniform magnetic field which we have, and the rod is moved in this magnetic field. Now let us say the rod was here initially, and this distance is now x1. Now after some time, let the rod is moved to some other position, because we are moving the rod in this direction. So this is x2. Now when the rod is moved, the new position of R will also change. Now this is the new position of R. So let x1 and x2 are the lengths of horizontal arms of the circuit at T1 and T2 respectively. Now let us calculate the area of this loop inside the magnetic field at T1 and T2. Next you write area of loop inside the field. Area of loop, because why we are calculating area, the change in flux is due to change in area of the loop inside the magnetic field. So area of loop inside the magnetic field at T1, let's say it is A1. It is from the figure, it is this length is L, it is given, so it will be the area at T1 is L into x1. This area inside the magnetic field, area of the loop inside the magnetic field, L into x1, length into breadth. Similarly, area of loop inside the magnetic field at T2, A2 is, now L is same, x1 becomes x2. Now change in area, dA is A2 minus A1, which is equal to L into x2 minus x1. Now you can also write it as L into dx. x2 minus x1 is change in length dx. Now therefore change in flux d phi is B into dA. Why? Because phi is B into A and B is constant because uniform magnetic field, therefore d phi is B into change in area, which is equal to B into L into dx. And rate of change of flux d phi by dt will now become BL into dx by dt. There is no change in B, there is no change in length L of the rod, it is constant given. B into L into dx by dt, and this dx by dt we can write it as velocity BLV. Now what is this d phi by dt? This is nothing but induced EMF. By Faraday's law, we have induced EMF induced EMF. E is d phi by dt. Now comparing these two equations, let me write this as equation number 1, this is equation number 2. So from equation 1 and 2, the induced EMF E becomes equal to BLV. This is the induced EMF. The induced EMF is given by BLV in terms of magnetic field, B the length of the rod and the velocity V. E is equal to BLV volts. Now what is the second question? It is to find out the second question is about to find out the force find the force required to move the rod in the magnetic field. We will continue in the next class.